Do you have any questions? How did you do on that assignment?
Felt pretty good.
So on the on the one that threw me down, what's my velocity at 8 seconds?
Was that the one with the velocity starting at 2 meters per second?
Yes.
I got 82.
Okay. Is that what you got, Isaac and Ryan? Zach?
Trying to find the piece of paper where I wrote that down.
Lena, do you have that paper? Can you show me?
Yeah. This is what mine looks like. Oh, hold on, sorry.
Okay. Hold on a second. My computer is asking me for something. So your numbers are wrong because you want to write the position down of where you are at the end, not how far you fell in that 1 second.
Okay, so I wrote like T 2 seconds equals 17 meters. So how should I write that then?
Well, your velocity is 7. What's your average velocity in those 2 seconds?
In the 2 seconds.
Isaac, did you get this?
I think I might be a little confused now.
Show me what you did. Can you show me what you did?
I didn't write everything out, but this is I don't know if I'm showing the right thing or if you can even see it.
Okay, yeah, see, so look at the first one. Well, before we do that, Isaac, I'll come back to you in a second. Ryan, did you get this?
No, I forgot to do it.
Zach, where's yours?
I couldn't find the paper, but I'm just quickly jotting down the work right now.
Shannon, did you do this? Shannon, are you there?
Yeah, I'm here.
Did you do this?
Oh, I think I forgot.
What am I supposed to do with that? How am I supposed to teach when you don't do your stuff? Isaac, the first one you did was 2 meters per second, right? That's the initial velocity. What's your velocity at 1 second?
Wait. Would it be 4 meters per second at 1 second?
Now, how did you get 4?
Well, is it 2 meters per second at 0, or is it 0?
Yes.
Okay. So let's see. I know there's an equation, but I'm assuming that it doubles at the next second.
How do you know what the next second is? You know what I'm saying?
I don't think I understand your question.
How do you know what the velocity is at 1 second? Talk it through.
Oh, at 1 second? Well, if the acceleration is increasing the velocity as you continue falling.
And how much is the acceleration?
10 meters per second squared.
Okay, so you started at 2. Well, you're going to be a second later.
12.
So what will it be at 2 seconds?
14.
No.
No.
What are you doing in the next second? You're still changing your velocity by the same acceleration. Right?
Oh,
And all of these things, the accelerations haven't changed.
would
right?
be 22.
Yeah, so what would it be at 8 seconds?
82.
Okay, right? That's what Lena said. So now look at the second one. What's the velocity at 8 seconds?
Negative 83.
No. Because look, which way do you start? -3. You're changing your velocity that way. So at 1 second, what would your velocity be? At 1 second.
It's either 7 or negative 13.
Okay, well, are you going faster up and up? Because that's what negative is in this case, going up, right?
Oh,
So
okay.
you were going up at 3, now you're accelerating downward though, right? So you'll be 7 going down. Do you agree that 7 and -3 are 10 meters per second apart,
Yeah.
right? So it's 7 going down.
Okay.
So what would the next second be?
17.
Right. What would it be at 7 seconds?
67.
Well, add one more.
Sorry?
77. Here, Isaac, in 8 seconds, how much will you have changed your velocity by?
From which number?
Here, hold on. Right? And I'm asking you, what if you changed your velocity? Well, we know that this is 10 meters per second times 8 seconds. So what that equals is 80 meters per second. But what's 80 meters per second?
The change in velocity.
What did you start with? So change this number by 80. It's going to be downward at 77. Right? Isaac, are you okay?
Yeah. Yeah, makes sense.
Do you see what you did wrong though?
Yeah, I do.
You were just taking the number, doubling it. Well, that's because you went 10, 20, 30, 40, right? But you're doing 10 plus 10 plus 10 plus 10, and you're still doing plus 10s. You just start with a different number. It's like if I said count to 10s, count by 10s, you'd go 10, 20, 30, 40, right? But, oh, no, wait. Count by 10s, but start at 2. 2, 12, 22, 32, right?
Yeah, that makes
Yeah.
sense.
So for the first one, it was at 2. And then later it was at 82, right? So how far did you travel in 8 seconds? What's that distance? What was that distance? What'd you get, Lena? Sam, did you do this? No. So
Would that be 90?
why do you say that? How do you know how far you travel?
Well, in the other example you had, you went from -3 meters per second to 80. And that was 77. So if you go from 2 to 92, that would make a difference of 9.
Sorry, no. Shoot.
Oh, 82. My apologies. That would be 80.
No, but how far did you fall?
80 meters, right?
Why did you get 80 meters?
Because you started at 2 and ended at 82.
How do I know how far I traveled?
Oh, wait.
Right, Lena?
Mm-hmm.
That's the formula? What am I trying to find this? So what is delta x equal to? You know that this is 8 seconds, right?
Mm-hmm.
What's the average velocity?
Is it 42?
How did you get 42?
I added our start of 2 meters per second plus 82 meters per second and then divided that by 2.
So you took the initial velocity plus the final divided by 2. Why can you divide it by 2? That's a good test question. Why can I divide it? Why can I do this?
Because it's linear.
Because the velocity increases linearly, right? When I graph out the velocity versus time, I get a line. It's a terrible line, right? And the slope of that line is the acceleration, which is constant. Which means if that's what my average velocity is, so 2 plus 82 is 84 divided by 2, which is 42. Then I go 42 meters per second. And that's going to be the distance I fell, which is going to be 336. Do you understand this? Okay, so here's the question then. When I've got this scenario, when I wasn't moving to start, how far did I travel? 320 meters. But every second that I'm falling, do you agree I'm going 2 meters per second faster? Repeat what I say.
Each second you're falling, you're going 2 meters per second faster.
How many seconds am I falling?
8 seconds.
8. So if I'm going 2 meters per second faster, every second, I will go 16 meters further. Which means that this distance formula that I gave you looks like this. What did we call this part? What did we call that part? That's the distance you fell because you were accelerating. What if I had no acceleration? What if gravity didn't exist? How far would I go in this time? Well, if I'm not accelerating and I'm starting at 2 meters per second, do you understand that I'll always be at 2 meters per second? An object traveling in motion stays that way. So if it's at 2 meters per second, it would stay that way. If it's what? And what do we call that? What do we call the motion like this? That's the inertial part. So that this formula in yellow is the more complete formula for knowing how distances are. But you better know how to apply this and understand this is the part because I'm going faster and faster and faster. Because I'm accelerating, is my distance traveled going to be linear? This number means it's exponential, right? It's exponential because I'm squaring it. If I were traveling at a constant speed, then I'd go the same speed and I'd go the same distance every second. But because I'm accelerating, the distance I travel in a given amount of time is this. So watch this. I'm going to do this really quickly in bad lines, but you'll get the idea. I will have traveled this far in that amount of time. I will have traveled this far in the same amount of time, assuming they're equal. In the same amount of time, I will go further because I am going faster. When am I going faster?
All the time, like as you're falling.
Okay, Zach, you're not wrong, but when am I going faster? Do you agree I'm going faster this way?
Oh, with more time, yeah.
But what do we say that? I'm going faster.
Later, you're going faster later.
Right? Do you understand what I'm saying? So I know why you said what you said, but this is what I want you to know. I'm going faster later because I'm accelerating. I'm changing my speed. Now, I want to redo this graph over here, okay? So watch. Get rid of the blue, get rid of the yellow. Oh, too much. I have to be more precise. Whatever. I guess I can do this. There. What is this line right there? How would you describe this pink line?
I would describe it as a tangent.
Okay, it is the tangent at that point. What is this point?
A point in time, like.
It's a point in time, and it tells me I am here, right? A point location. What does this tangent slope tell me? Ryan?
It tells you the velocity, the average velocity.
No. It doesn't tell you the average velocity.
Oh, would
Does it tell you the final velocity?
No. It tells me V, which if you see V without the AVE, see over here, that's average. What does that mean?
it's the instant?
It's the instantaneous velocity at this moment in time. So the slope of the pink line, which is tangent, the slope of the tangent at that point is the instantaneous velocity at that point in time. Write that down. Go ahead, Lena, read me what you wrote down.
I got that you said that V alone is instantaneous velocity.
But what else did you write down? What did you write down?
I was
Isaac?
writing down. Oh, sorry. Go ahead.
Isaac, what do you got?
I wrote V is instantaneous velocity at that point in time.
The V is the instantaneous velocity at that point in time. But what's the instantaneous velocity at that point in time? Because that's what I think you missed, Isaac. What is the instantaneous velocity at that point in time? At this pink dot right there. What tells me the instantaneous velocity? You're missing the first part of that. Anybody else?
The slope of V
The slope
of the tangent line.
slope of the tangent line at that point tells me the instantaneous velocity at that moment in time. Do you have that? What did you write down? Read it back to me, Sam.
I have this V is the instantaneous velocity at that point in time.
Well, you missed what we just went through. What are you looking at? What were you
I was
watching?
writing it down.
What did you miss?
I missed the second part, what you just said.
Lena? Tell us
It's
what you
the
write down.
slope of the tangent line.
Say the whole thing, please.
Oh, okay. The slope of the tangent line, which is V alone, or I don't know how to say it because I just wrote. So, the slope of the tangent line is the instantaneous velocity at point in time.
At some point in time, right? And a point in time is a moment at then, right? It's at that moment in time. And it's the slope of the tangent line that tells me what that is. Now, what's the formula for the slope of this tangent line? What's the formula?
It's just change in x over change in time.
False. If I said change in x, then I'm looking at the average.
Oh, just x over t.
No. What do you have, Ryan? What is it?
So the velocity is just going to be the slope of it, which is the given x over the given t, or the
No.
instantaneous
This
x.
is not what it is. That is not what the formula is. Because this x could be 2 meters and this time could be 3 seconds. Are you telling me it's 2/3 of a meter per second? That doesn't seem right. That is not the formula. This is not right. What is it supposed to be? Isaac, man, what are you getting at? What are you thinking?
I'm not sure.
Shannon, can you put your camera on? Shannon, are you there?
Oh yeah, sorry. One moment. Yeah.
Guys, look at this right in here. What is this supposed to be?
Well, okay, hold on. I'm gonna try to brainstorm out loud. So if you're trying to find the slope, wouldn't you need 2 points? So you would have to have a change.
Is that what I have? This is at a point.
Hmm.
Lena, you're thinking, you
Mhm.
missed the point of what we talked about. We talked about it last week. You're missing what you wrote down. You've done these notes. This is
Mhm.
not new.
Oh, would it be dx dt?
What do you have in your notes?
I have v instant equals dx dt.
Right, and the thing is, I don't write instantaneous.
Mhm.
I just put V. So you're saying, what I'm saying is that V is equal to dx dt. V average equals dx, I'm sorry, delta x over delta t. How many points do I need for this?
2,
How many points do I need for this?
1.
1.
And that's why it's a tangent, because how many places does the tangent line intersect? The answer is just 1. So the slope of the tangent at a point in time is the instantaneous velocity at that point in time. In other words, if I were to graph let me get rid of this. If I were to graph velocity versus time, I said at this point in time, that's this point in time, and that would be the velocity at that point in time. And it's the slope of the tangent for the reasons we went through last week, getting smaller and smaller triangles till it's infinitely small. Okay, what is happening at this point in time? Do you agree that there would be a tangent line? What's the tangent look like? What does the orange tangent line look like compared to the pink?
Has a
It's steeper.
steeper slope.
It's steeper, which means the velocity is bigger, because at this point in time, at orange T, isn't the velocity greater? It's increasing linearly, so that slope, look at this, guys. You need to watch my hand as I'm going from right to left on this green curve. It's doing this. I'm going faster and faster, and the slope is getting stronger and stronger. So I asked you last week, I said, walk this way. So back your camera up, turn it around. I want to see you walk this way. So make sure you have some room that you can walk and away from the camera so I can see what you're doing. Or Aaron, in your case, can you wheel that way? Or maybe make your dad walk. That might be a good thing too. Yeah, you can wheel it. There you go, Aaron. Can you wheel it this way? Isaac, what do you think?
Oh, do you want me to do it?
Yeah, let me just see what you're thinking.
Okay, so.
Do you agree with him? Zach, what do you think?
Can't really see from back here.
What is this point? Give that point a name.
It's the origin point.
Okay, what'd you say?
Oh, it's the origin point.
Yes and no. I think there's a better word for it.
That's start.
That's the starting point, isn't it? What do you know about the starting point? I'm starting from the beginning.
Start at 0.
And I'm starting at 0, right? So wherever you started, so Isaac, you're there, whatever, you're starting there. And then what's the time? Time equals 0, right? Start. Okay. What is this point? And we'll call this point A. What do you know about what is happening at point A?
That's the farthest distance that you walk in that amount of time.
Ask Isaac to explain that if you don't understand it. You all understand what he said?
Isn't it kind of like lambda max that we were doing before, except this is not with wavelengths?
So Isaac, say it again.
That's the farthest distance that you go in that amount of time.
So I've gone this far, right? At this time, I am this far, this arrow far from the start. What has happened inside of here?
You sped up to that point.
How do you know? Did I speed up? Zach said I'm speeding up.
Well, you speed up for the beginning half and then you slow down as the arc.
Okay. So do you see that this slope here is actually, it looks like I'm fastest to start and I'm getting slower, right? So this is starting out fast. So you're not starting from rest, are you? When am I at rest? When am I at rest?
At the very peak. At the
At,
very
at,
peak.
at time A, right? Because what's my tangent at that point? It's horizontal, which means it's zero slope, which the slope of the tangent is the velocity. So what does that mean? The velocity is zero. Now, if I started at zero and I sped up, wouldn't I do this? That's going faster and faster, and then, right? The steepest this curve is when I'm going fastest. So because my initial velocity, look, do you agree that's my initial slope, like right there? I'm not starting from rest. So I could be running like this, right? I could be running and I go start. And then I'm slowing down as I move to the end. So Isaac, you walk the correct location, not necessarily the correct speed, but I didn't expect anybody to do that. Now, what happens after point A?
You start moving back to your starting position.
Do you agree that this is my slope there? And that slope is a negative slope. So you're going this way, and then you go the opposite direction. And then what is this point?
That's the same point as when you started.
That's the same point that when I started, right? So I started here, I go, and I come back. And then I walk in a negative X direction. So, by the way, here, you guys can have a seat. How many dimensions is this graph?
It's two-dimensional.
Zach says three-dimensional. Do you agree?
I think it's two-dimensional.
All right, Isaac's saying 2 dimensions. How about the rest of you, Shannon? What do you think?
I think it'll be two-dimensional.
Ryan?
Isn't it just one dimension because it's just going back and forth?
It's
I don't
one
think
dimension
it's
because
three.
what is one dimension? It's a line. You're going this way and then back, right? You're doing this. You're going in this forward or backwards direction. You're a one-dimensional thing. Now, you could say that time is a dimension, but really it's just you're walking in a line. If I were walking in a plane, like if I could turn left or right, I would have to draw this graph in 3 dimensions. And if I were walking in 3-dimensional space, how many graph axes would I have to have?
3.
I'd have to have 4. So do you know how to draw a 4-dimensional graph? Because if you say yes, you're really, really cool, because I can't think outside of 3 dimensions. But do you understand that if I'm plotting out my location in time, I have to have 4 dimensions, 3 space, 1 time.
So if this is two axes, right?
This is 2 axes. One of the axes is time. The other one's a single space dimension. So
Oh, okay.
this would be 3-dimensional. So a 4-dimensional, and does anybody know how we do that? Since we don't know what a 4th dimension looks like. We use something called a matrix. So we can do more dimensions in a matrix because we can apply the mathematics to it. What we can't do is visualize it.
What
So-
about for designing, and how many dimensions is that?
Well, it's 3
3, right?
dimensions, but you can't do it over time unless you animate.
Oh.
So you can animate a 3-dimensional object. That's what animation is. But you can't graph a 3-dimensional location in time. Now, the funny thing is, I once took a class in this. So imagine that I have a 3-dimensional object, like my phone or something, right? 3-dimensional object. Do you agree if I shine light on it, what does it create on the desk? Do you agree it creates?
Shadow.
So that shadow is some sort of a figure that's 2 dimensions. Do you understand that 2-dimensional figure is the shadow of a 3-dimensional object? So what if I said this phone is a 3-dimensional shadow of a 4th dimensional object? Would that blow your mind? Yeah, because I did an entire class about that concept. I had no idea what I was doing in the entire class, but I got to see somehow. But it just gives you some idea. So let's go back to what we have on the screen. So what's the next important point on this graph? What's my velocity at point C?
It's negative. It's the same. It's 0.
0, right? Because the tangent is still, it's horizontal. It's still 0 slope. But now, what does this point represent? It's the furthest I am in the other direction. But what do I do right after point C? Do you see that my velocity is increasing now? So I'm speeding up and going faster. And then what is this point here?
That's the starting point.
I'm
Yeah.
back at the origin, right? I'm back at where I started. But then I keep going. When I get to here, what's different? Like when I'm here, how far from the beginning? I'm that far from the beginning, right? I've been there before. So Isaac, you went this way and then back, and then you went this way. But what did you keep doing? You kept moving further away and further away. So now this line is now horizontal, which means what? What's my velocity?
It would be constant, right?
Well, if it's horizontal, what's the velocity? It is constant, but what's the value of it?
0.
And in other words, if I have no velocity, where am I?
In the same position.
Same position, right? So your graph of x versus t throughout your life will eventually end here. What is this called?
Flat line.
This is death, right?
Yeah.
That's what happens when you die. And actually, that's not what happens. It's actually like this. Anybody want to know what that little place is? That's when you're in the casket and people your pallbearers have to carry you and bury you. Because then you get put into a place. And hopefully you stay there for a while. Unless, somebody comes and robs your grave and you do one of these things again. Because once you're there, time keeps going forward. Your velocity is 0 and you stay in the same place.
Well, all things considered, we're all moving though.
Well, that's true. If you look at it from a frame of reference in outer space, we're spinning around in a circle. So we're always moving. And then we're traveling around the sun, and the galaxy's flying through space. So I guess we are always moving. But that's where we come about, Sam, called frames of reference, with reference to the Earth.
Oh,
Unless you're on the side of a hill and there's a mudslide, and then you come down the hill. So always possibility that you could still move. Hey, what's the steepest this can be? I'm going to blow your mind again. Can the line do this? By the way, here, what does this line represent? Why is that God? Lena, you're muted.
Yeah. Oh man, that's so hard to explain.
Why is this vertical line representing God? There's an attribute of a transcendental God. It's called
it never ends.
omniscient,
omnipresent.
omnipresent. That's what it is.
Omnipresent means I'm everywhere at one time. So at this time, where am I? Everywhere, right? That's what this line would be. So what's the steepest this line could actually be?
Can't be vertical though, right?
It can't be vertical because then it's not a function, meaning you're every place. Where are you at this moment in time? You're every place.
Right.
So what's the steepest this can be? And this is where your mind's going to get blown. What's the steepest this line can be?
Is it the speed of light?
How much is that? Remember?
I forget.
3 times 10 to the 8th meters per second. Aaron, do you remember that?
Yeah.
That's the fastest it goes. But here's the problem. You know what this line actually becomes? It actually becomes vertical. Do you know why? When you're traveling at the speed of light, what happens to time? Time gets slower and stops. So if you're traveling at the speed of light, you can go all different places at one time because time's not going forward. Isn't that cool? Just, those are just blow your mind thought processes.
It would remind me of like a scene in like a movie.
A Beautiful Mind, when you're thinking weird thoughts. Anyway, I just thought I would show you that stuff. What I really want you to do is just understand how this graph plots you out. Does that make sense? So Isaac, you did a pretty good job reasoning out what you were doing. Does it make sense to everybody?
Yeah.
Beautiful. Okay, so hold on a second. I'm gonna hide that. And where are you guys? Oh, I know where I am. Stop share. Recording, am I recording now? Share screen. I want to do something that I think might be beneficial to a lot of you. And that's creativity. You see, when you learn how to think and you find problems, one of the things that I really like to do is I like to solve problems rationally, but it offsets to me a creative side of my mind. I like to create something different. I like to be art. So one of the things that we're doing on our website is we're creating stuff. Now there's a lot of programming. I've got people who do all the logistics. I'm just the idea guy. I'm like, I want to see this. I don't like this. I want to see this. It's first time I get to really manage, and I'm getting better at it. It took some time, but it gives me a creative sense. So one of the things that we did, Sam, you would know this. Remember we've been doing some forecast soundings?
I see you added the blue parcel.
I know, right? So oh, let me do this just so I can use a fun sounding. So when I go out here to the future, here's something interesting. I got some cape in this. But what I did is I went to a blue parcel so that it works with our stuff. And I changed the dew point so it's not such a bright green, but it looks a little bit, see, to me, it's just aesthetically better. But there's something else that I did. And I just thought I would see what you guys thought of this. I want to see how your mind creates. You know how we've always did the environment's red and the parcel's blue. I want you to see something with this parcel over here.
Interesting. When I was looking at models this morning, I saw that and I was like, that was him.
Yep, I've been wanting to do this and make it readable because it was always confusing to me. I didn't see it and now it's more obvious. So Sam, you can talk about this sounding here and what do you see and what do you learn from it? What do you guys see, the rest of you, about this parcel and sounding that looks weird, that you've never seen before?
Well, there's like, what color is that? Like cyan. There's a
Yeah, I
blue
mean, just
one.
call it blue and red, right?
I think she's talking about in the middle,
Yeah,
between the green and red.
This, okay, since you brought it up, this thing here, that's the wet bulb temperature.
Oh, okay.
So that plots up the wet bulb temperature. So Sam, if you want to know where the wet bulb 0 is, that's where it is for
That's
hail.
where the purple
Right? When
dash line.
you have low wet bulb zeros, and you're gonna get some big hailers.
Well, that's sounding just,
This purple
this
line,
one specifically is telling me, dry in the lower to mid levels. So maybe some hail.
yeah, well, I'm not saying anything about this specifically, but I'm saying that's what wet bulb temperature is. But remember, that's what we've got. But what else do you see that's really different? Do you realize that every time we did a parcel, we did the environment and we did the parcel? Something like that, right? Do you see that the parcel always started from the same temperature as the air? Does that look the same? Here's the temperature of the parcel. Here's the temperature of the air. What's this red dash line? You guys have any idea what that red dash line might be?
Would that be surface heating?
No. That red dash line is something known as the virtual temperature. Now, do you remember what we did is we would lift a parcel of air. It goes up dry adiabatically to the LCL. So there's the LCL. And then it goes up wet adiabatically. So that's that blue line. That's what it is. The question is, at this point, at right there, let me ask you this. Is this parcel buoyant? What would you answer? Is it buoyant?
I don't know.
I mean, at this point, right, I'm asking you a question. I don't know if you know what the answer is or why you think the answer is. So you have to tell me what you think, right? You have to actually verbalize an answer to me. So what do you think, Ryan?
I don't remember when something is buoyant.
Okay,
It's when it's less dense.
Okay, so interesting way that you did this, Ryan. This is an interesting thing that you just did. So as a teacher, I'd go, well, what is buoyancy? Now, you do know that we've gone through this, right? There was a while back. So I'm asking you if it's buoyant. So the first thing you need to say in your mind is, do I understand what buoyancy is, right? I want you to think about, Isaac, you're solving some problem, doing whatever. You have to know the problem. You have to understand what is the thing so that you can solve it. You really need to know this stuff. So what is buoyancy? And then Ryan, you gave me an answer. And what does that mean?
Is it when the parcel is less dense than the environment?
It is less dense than the environment. Do you agree? How do we know if it's less dense? That's my next question. I have a sequence of thoughts. So how do I know if it's less dense? What's the answer to that?
The temperature, because colder temperatures are more dense than warmer
Okay,
temperatures.
so you look at the temperatures, and what are we comparing? The temperature of the parcel and the temperature of the environment around it. So there's the temperature of the parcel. Let's say 20 degrees Celsius-ish, something like that, whatever. What's the temperature of the environment? Well, over there, right? Doesn't the environment look colder than the parcel? So you would say the temperature of the parcel is warmer than the temperature of the environment, so it's buoyant. And yet, when it becomes buoyant, you'd say that's Kate, and the air would start to go up. So that should have been at the level of free convection. But why is the level of free convection so much higher? Why is this the level of free convection and not way down here someplace? And the answer is, it's warmer than the environment, but it's still not buoyant. See, I've been lying to you.
I have a
Right.
question though.
Huh?
I have a question. So this sound, so the ones you've been making for us,
Mhm.
you've been putting NBE and PBE in them. I see no NBE in this one. So
There is sort of NBE right in there. They're close. There's not much. A little PBE, a little NBE. But where does how about this, Sam? Where does the PBE start? The PBE starts at the LFC.
okay, so you don't use the environmental temperature. You use the virtual environmental temperature, right?
But what does that mean? Yes. So really what I'm saying is I am not using, like Sam said, I'm not using this line. That's the actual temperature line. I'm using this red line. Now, if I look at that red line, do you agree that they start to separate here? That's why that's the LFC. But the question is, why is it that the actual temperature here, for instance, is colder than the parcel temperature? What does it mean to have a virtual temperature? Well, here's the problem that I've never told you. The box of air has a density which is a function of temperature. But you know what else it's a function of? What's W stand for? You remember? What's W stand for?
Isn't it the mixing ratio?
The mixing ratio, which is, what does that measure?
The amount of water in
Water.
the atmosphere.
Water
Vapor,
right? What do you understand that putting water vapor in the air changes the density of air? I have two boxes, box A, box B. Everything about the two boxes is the same. Temperature is the same. Volume, number of molecules, all the same. The only thing here is B has more vapor. The density of A compared to the density of B, how do they compare? Putting vapor in the air, does it make the air the same density, more dense, or less dense?
And make it more dense.
Well, what do you think, guys?
More or less.
Do you understand the question? Does putting more vapor into the air change the density of the box? Now, do you know the answer offhand? Sam says he thought one thing, but did you notice that from his question or the way he said it is uncertain? So now you have a problem, and you've got 7 people here to solve the problem. Let me hear you discuss the problem and solve it. Now you've got to come up with ideas that go beyond anything we've talked about. Because we've never talked about this. So you can draw from any experience whatsoever. So talk to each other now. Have a discussion. What are you thinking, Isaac? Can you guys extrovert for a little bit? You know what I mean by that? What do I mean by extrovert?
Step outside of our comfort zone and talk.
Yeah, no, that's not really what I mean. Extroversion versus introversion is a way of thinking about thinking. If you're an introvert, where are you thinking? Inside your mind. Like Lena's over there going, her eyes are up there. Remember we talked about this the other day? Eyes are up there and she's like, oh, she's thinking. I want you to extrovert. I want you to think out loud. You have the ability to think out loud. And unfortunately, in all of your fields, in anything that you're going to do, you're going to have to think out loud. If you're having a discussion with other people, you have to verbalize your stuff. It's amazing how many times I talk with people who can't think outside, and then there's no constructive dialogue. So I'm asking you to think outside of your brain and give me some ideas with each other. And I'm just going to listen in.
Aaron thinks the box with the water vapor is less dense because the water vapor is less dense than the air itself.
Respond.
I think the water vapor would make it more dense because wouldn't it eventually turn into liquid water, and wouldn't that cool quicker? Which would then...
Do you realize that a thunderstorm is a cloud made out of liquid water? Lots of small droplets, but do you know how many billions of tons a thunderstorm weighs? Think of the rain falling out of a thunderstorm and how much. Think about a thunderstorm dumping rain on an acre of lawn. Do you agree that it might be an inch deep if it was just over 1 acre of your yard? How much would that water weigh? That was all up in the sky. Thunderstorms are really heavy. Water is really heavy, but water is still made out of molecules, and those molecules, whether they're in liquid form or in vapor, are the same weight. So notice that Aaron and Zach have contradictory answers. Sam, you were questioning, you agreed with Zach. Do you have any other thoughts on this?
Well, I was thinking that, if if it has more vapor than the other box, and that's the only thing that's different. If you have more vapor, and no matter what vapor or liquid, it still weighs the same, you said, right?
Mhm.
So if it has more vapor, then it must be a little bit more dense. Because it would weigh a little bit more.
Okay, so you're using dense and weigh, and Aaron, you used the word density. So here's the question: what does water weigh? You should know this because we have done this. What are you thinking about when I ask you that question? What do you think I mean by that? We'll go back to you, Isaac. What do you think? How much does water weigh? How do you answer that question intelligently?
Let's see. Whoa. Are we talking about just liquid water or water vapor?
What matters?
Uh,
Does a ton of bricks or a ton of feathers weigh more?
They weigh the same.
Because it's a ton. So does a kilogram of liquid water weigh any different than a kilogram of vapor?
No.
But what does it mean for water to have a weight? What do you call that?
it has mass.
What is the mass of water?
The amount of water that there is.
Yeah, I don't think you're getting what I'm trying to get you to say. I'm leading you to in a direction. What do I need to know? If I said there's 1,000 marbles in the jar, they're all the same, 1,000 marbles. How much does it weigh? What would I need to know?
The weight of one marble.
Okay, so I'm asking you how much does water weigh? What do I need to know?
The weight of one molecule.
Wouldn't I need to know the weight of one molecule? What weighs something in a molecule? The atoms.
The atom.
What's water made out of? What is the formula for water?
H2O.
So how much does a hydrogen weigh?
About one.
One. How much does oxygen weigh?
Isn't it like 18?
16.
16.
So water is 18, right? A molecule of water weighs 18. What's the rest of the air made of?
Nitrogen and
What's the chemical symbol for nitrogen?
is it just N?
No. Atmospheric nitrogen is not just N. What is it?
N2.
N2. What's oxygen's chemical formula?
O2?
O2. Now, do you agree? What did we say O is?
16.
16. So what's O2 weigh?
32.
32. What does water weigh? 18. Do you agree that a molecule of water is lighter than a molecule of oxygen in the air? Nitrogen. Anybody know what nitrogen weighs? Do you know what it is offhand, anybody? Nitrogen is an atomic number of 14, so N2 is 28. So 28 for nitrogen, oxygen is 32, and then water's 18. And then there's also 1% of the air is argon, which is like 36. Okay, so now imagine that I have a brick, a solid brick cube with 100 bricks in it. 78% of those bricks are going to weigh how much?
It was 28, right?
28 nitrogen. So imagine that you have 100 bricks, 78 of them weigh 28 kilograms, whatever. Okay. 21 of those bricks is going to weigh 32.
Yeah, 32.
And then one of those bricks, argon, is going to weigh 36. So do you agree that if I take the entire mass divided by that brick, that cube that I have of bricks, that's the density of it. But now I want to put water into it. Putting water vapor into the air is like doing what? What does that mean to put water vapor in the air in terms of this brick structure? How big is that box? 100 bricks. So if I start putting water bricks in them, and how much do they weigh?
18.
18. What do I have to take out? Let's say I want to use 2 water bricks. Do you understand I have to take out some heavier bricks to have room for it? So I have to take out 2 larger bricks and replace them with lighter bricks. What will that do to the entire weight of this brick cube? Same volume, but it'll weigh less. When I put water vapor in the air, I make the air less dense. So what I'm saying on this chart is that over here, the air is more dense because it's colder. But do you also agree that the air's got water vapor in it? And the amount of water vapor in it makes the air appear less dense. And that's what the red is. The red dashed and the blue dashed are actually truly comparing the density content. So where truly does the air start to become less dense? Here. That's the LFC. So Sam, we're talking about tornadoes, right? That pot, and this is from a different class, but that parcel of air, it might be saturated there, but it doesn't accelerate until it gets to here. And then the amount of acceleration of this box is the amount of CAPE. CAPE is the energy used to accelerate the air upward. So when the box gets here, what is the box's initial velocity? About that. I start to get this energy that accelerates the air up. So do you agree that the air is going up faster and faster? Does that make sense? So that's the CAPE is accelerating the air up. Where does the CAPE start? Not till the LFC. But that means it's in a cloud and it's not doing anything. So I'm not going to, so from those of you taking 1115, we're not going to stretch a tornado because I don't have enough down low. So when you look at a sounding like that, that's how you have to interpret the sounding. But that's pretty advanced, wouldn't you think? But I want to ask you something. The virtual temperature says if I put water vapor in the box, in the air, that makes the air what? If I put water vapor, what does that make the air? Answer. When I put
Less dense.
it makes it less dense. What else could make it less dense? Making the temperature warmer.
Wow.
So what I'm doing here is I'm saying Rather than worrying about how much water vapor I have in the air, let's just make the atmosphere a different temperature to account for it's less dense because of water vapor. That's the virtual temperature. I just adjust the temperature to pretend it's the same drop in density as having vapor in the air. But does that make sense that water vapor in the air makes the air less dense? Now let's think baseball. Any of you watch baseball? Does the baseball travel further in humid air or dry air? The answer is, what do you think?
Well, wouldn't it be humid air because there is
Would
less
it be
dense?
humid air? Sure. If it's humid out, the balls go further because there's less resistance. There's less mass there resisting the ball. The only thing is, what happens when you get to around 80% relative humidities in the air? What sometimes exists on a hot summer day, hot, humid day? What do you see in the sky? What's that stand for?
Haze.
That's haze. Haze are droplets of water that exist for a little bit and then evaporate again. Not like a cloud that stays. So when I hit a baseball through haze, the ball may get waterlogged. And if the ball is wet, then it doesn't fly very well. You don't hit it as much. It doesn't have as much elasticity.
Would haze affect the environment for severe weather?
No, because haze, remember, just because they're droplets of liquid water doesn't make it any more or less dense. When I take a parcel of air and I lift it, and the air is expanding, and then there's a cloud in it, whether the cloud is in it or the vapor's in it, it's the same density, because it's the same weight, because it's the same number of molecules. Because what kind of a box is this? It's a Vegas box. And whether they're vapor or liquid, it's the same molecules. Now, why did I do this with you guys? How well were you able to follow this discussion? Give me a hand sign. How well were you able to kind of follow and figure and do this? Did you feel like you could follow me? You didn't necessarily need to know it, but when I told it, did it make sense? Okay, why do you think you've learned something? Why did you learn something? What do you think the answer to that question is? Shannon, why did you understand what I was talking about?
What is this explanation, I guess?
What did you say about the explanation? I'm sorry, I missed it.
I said explanation.
But why did you learn it?
Um,
Why did you say that seems to make sense to you?
there was connections. Mhm.
Okay. What do you think, Isaac? How about you?
Yeah, I mean, sort of what Shannon said. You can make connections with things that you learned previously in
Did you
class.
were you paying attention?
Hmm.
Aaron, did you what's your number, Aaron?
You said 4.
4? Did you understand that, Aaron? Were you all paying attention? Sam, why were you paying attention?
Well, because I I really am interested in this stuff. And
Okay, so you're interested in this stuff. You have a purpose for it. How about the rest of you, Shannon? Were you interested in it?
I guess.
Why do you think you might be interested? Did your brain seem to like to be challenged? Did you like the puzzles? Did you like the feel of going, I don't understand, to I understand? Do you like that feeling of learning? Okay, so in other words, what should motivate you? Where should the motivation come from? You know this word? Are you familiar with this word, guys?
Mm-mm.
What does that mean? Intrinsic. Just do a web search on that. Go take a look at that. You're all by a computer? What does the word intrinsic mean?
Belonging, naturally essential.
Do you want to learn? If you are intrinsically motivated, you just want to know stuff. You find interest in it because you want to know. Wanting to know is just your brain going, I kind of like learning. It can be anything. I told you that earlier this year, I was watching TV. I'm watching ancient American civilizations, like in the years 800, in what is now known as North America. Where were their indigenous people? I was watching this. Do you think I naturally care? Do I have any reason to affect my life? It was just interesting to me, and I was listening to it, and I was interested, and I was motivated to learn about it. When I asked you earlier what motivates you, carrot or the stick, and Lena, you kind of have this. It needs to be from within side of you. I care and I want to learn. That's it. You put that into every single one of your classes, you're going to do 30, 40% better. Because then the teacher doesn't have to try to keep your attention. You're focused, you do the stuff. Here, give this assignment. Oh, this is cool. I get it. I get it. And you might get frustrated if you don't get it, but then frustration can either motivate you, that's a stick, or you can at least ask questions about it. If it's too much frustration, what do you do? What do you do if there's too much frustration?
You give up.
Do you ever give up on things? Yeah, I can't get this, right? Then you become defeated. Does it feel good when you give up on I can't understand this, I give up. How does that feel? Kind of sucky? Okay. Intrinsic motivated people never give up because they go, no, I want to know. I don't have to give any reason. And then you start being an annoyance to me by saying, wait, explain this again. What? What is that? And when I have annoying people in classroom who demand to know, they're the best people to have in class because they're always wanting to know and they're easy to teach. And the reality is somebody like that doesn't not get it. You know why? Because the reality is most of your problems are not because you're a 2 or a 3 in your intelligence. Well, we all have different intelligences. Your problems are all by the motivation that you have. Sam, I think that's true for you. You know the goal, you know the goal line, but you've got to find that internal clock to motivate you to get to that goal line. That's what it's got to hurt, is when you're not doing that. So we have been doing some good stuff on accelerations. So what I'm going to do here, let me take a 3-minute break so that we have a good fresh half hour where you're a little bit rested and ready to go, because I want to review what we did so that we go into the winds coming up. And you'll see where all this kind of takes us. So I don't have to stop share, I just need to pause. Where are you guys? I am pause, resume recording. Okie dokie. So let's do this. I'm going to draw you one little thing first. And this is called Moses's fish tank. Do you guys know who Moses was? What are the things about Moses?
He split the sea.
He split the sea. So this is his fish tank. So basically what I'm saying is that this is Moses's fish tank. His fish tank looks like this.
I know where this is going, I think.
Okay, so there's all the water in his fish tank. Oh, it's a fish tank, so we gotta draw a little fish.
We're not going to shoot them like we did to the monkey, right?
Oh, we're not going to shoot the fish. That'd be terrible. Now, what's air pressure defined as?
The weight of the air above us.
What's water pressure defined as?
The weight of the water above us.
Do you agree that there is higher pressure on the left side of the fish tank on the bottom and lower pressure on the right side? Right? High to low pressure. Now, this is silly if the water were looking like that, because we know that's not the way it would. What would the water do without the intervention of God?
It would slosh and come back to equilibrium.
It's going to come back to equilibrium. It'll slosh, which is interesting. It's interesting that you would say that. It's going to go back and forth. But it tries to go to equilibrium. Do you agree that the water is going to fly from high to low pressure? How fast will the water move depends on what? How big the difference in the pressure is. So this is what we illustrate as a pressure gradient. Now, do you remember a gradient? What's the definition of a gradient? What's the definition of a gradient? This goes back to Math Lab 1, if you don't. Shannon, go ahead.
Was an increase or decrease in I don't know, an increase or decrease in like a certain amount of mass?
Well, there's something you need to know, the definition of the word gradient. This was on test 1. We did this on test 1. Do you know the definition, Aaron, what a gradient is? Did you find it in Math Lab 1? Do you guys have access to that? What do you guys have? Did you find it?
Haven't found it.
It could be in your notes.
It's a change in pressure over the change in vertical, or a change in pressure over the change in distance.
No, okay, first of all, it's not a change in distance. Look at earlier in the thing, it says what a gradient is. It's a change in something over
Change in location.
Change in location, which is a distance. So a gradient is a change in something over a distance. Okay, in this case, it's a pressure gradient, which means it's the change in the pressure over the distance from here to here. And what would that, how would I write that? The change in location.
Delta X.
Could I have written it this way? How many points do I need here?
2 points.
This is where?
1 point.
At 1 point. Right. So the pressure gradient is a change in pressure over a distance, over a change in the location, X. Now, what is this?
That's the pressure gradient with like altitude.
This is the pressure gradient as you go up, right? Or this.
That's a question.
What's the question? How does the pressure change as you go up? Now think about this for a second. We talked about the box. And do you agree that the pressure down here is something? What's the pressure up here? Less. right? So this box wants to go to low pressure. So it wants to go like this from high down here to low pressure. Do you agree that this is a force? The pressure gradient is a force. And what makes it a force is we do, and I'm just going to write it -1 over rho. Force is a mass times acceleration. A force divided by mass is an acceleration. Mass is in the bottom. So that's what this is. I'm writing them in terms of acceleration because density is mass over volume. Okay, we're not going to worry about that right now. But the idea is that what does the air want to do? Sitting around outside, which way does the air want to go? What does the air want to do naturally? It wants to go up because there's less pressure up there. Why doesn't it go up?
Because of gravity.
Which makes gravity act
Down.
So we have an upward force of pressure gradient, and we have a downward force of gravity. So we say -1 over rho dp dz equals gravity. Or we could say dp dz equals -rho g. Right? Do you agree that these are the same? This is known as hydrostatic. Okay? Hydrostatic. It's a balance between upward vertical pressure gradient and gravity down. So what's the net force on a box of air? What's the net force on this air? Do you agree that this is the same size as this? So the net force is 0. So the air at rest stays at rest. Until what? When does an object stay at rest? Until when?
Until a force is acted upon it.
You're missing a word.
Oh, shit.
Until what kind of force? Hey, everybody look at this. Do you see this picture? Do you see, is there a force acting on this box of air? There's two forces. One's going down, one's going up. So there's a force acting on it, but there's no what force?
There's no outside force.
No, that's outside to it. There's no Newton's first law. What does it say in Newton's first law?
No.
There's no net force. There's no net force because gravity plus pressure gradient equals 0. Okay, gravity is based on the Earth's mass, right? So that's always constant. What would make the upward force less? What would make this force less? You guys know what I'm talking about? Ryan, what's your thoughts right here?
So I think you could if you wanted to lower the force, you could increase the pressure inside of the box or decrease the pressure above the box.
I know what you're saying. What I want you to think about is this. I want you to think that this is the case. The force, the PGF, in the vertical is -1 over rho dP dz. Do you agree this is A equals B over C? So if the pressure gradient is bigger, that means the density is less. If the density is more, the pressure gradient force is less, right? So this force upward becomes smaller if the air is more dense. If the air is more dense, who's going to win this race? Gravity's going to want cold air to come down. What if it's less dense? What does the upward force do? It goes bigger up. There's a net force up. What does the air start to do? It goes up. Buoyancy, you asked, what's buoyancy? You're right from what we talked about, but this is buoyancy. Warm air is less dense and it wants to go up because it's a smaller force. I mean, it's a bigger force going up because density is inversely proportional to that force. So density changes, creates a bigger pressure gradient force, and that's why air wants to rise. Got it? Does that make sense? Isaac, what do you think?
Yeah.
All right, let's look at this. This is a map view where I'm looking at north is to the top. And I'm saying that this is some isobar, line of constant pressure, and this is some larger pressure. So this is no longer, look, guys, this is not up, this is north this time. So imagine that I put a box of air right here. Initially, the velocity equals 0 meters per second. Which way, what forces are acting on this box horizontally? Remember how with the bullet, we could separate the horizontal and the vertical? With this, we're saying, let's just look at the horizontal on this. Which way, what forces act on this box?
Would one be the Coriolis effect?
Okay, you're saying something, Coriolis force. Now, how many of you think the Coriolis force is acting on this box? Ryan says no. Zach obviously says yes. What do the rest of you think? What do you think, Shannon? What did you say?
No.
Why not?
Because it's not in relation, I think.
What does that mean?
I'm like in relation to like above the parcel.
The parcel is just a box of air. It's just molecules, right? They're things that act and move by forces. Is the Coriolis force acting on that air? Zach, why do you say yes?
Well, I remember like from the homework over the weekend, it was like the pressure gradient and the Coriolis force would like balance it out.
Okay, so you did something over the weekend, so good for you. Let's go back to this though. What's the definition of the Coriolis force that I gave you in class for the very first time we saw that?
It wasn't like a real force.
Okay, is number one, it's an apparent force, it's not real. What else did I say? What does it cause?
Objects to move to the right in the northern hemisphere.
No, you're missing a really important definitional word. What does it say the Coriolis force does? Lena?
Deflects.
Deflects what?
Causes moving objects to
Oh,
deflect to the
It caused moving objects
Oh,
to go to the right. What's the initial velocity of this air?
it's 0.
0. So it's not moving, so it can't go to the right.
Okay.
Is there a difference in pressure? Yes. So there must be a pressure gradient force. Now, from now on, the pressure gradient force will always be drawn in blue. Rule number 1. Are you looking at your notes from the class? Rule number 1. What's the rule? What's the rule number 1 in the classroom notes that I gave you?
The pressure gradient force always acts from high to low.
Do you see that this pressure gradient force is pointing from higher pressure, south, to lower pressure, north? Now, it's only south and north because that's the way the isobars look right now. So high to low pressure is always perpendicular to the isobars. So you need to remember that this is always perpendicular, right, to the isobars. And it points to the north. So an object at rest stays that way until acted upon by a net external force. An object in motion does the same thing. This is at rest, but there's a force acting on it. Will it stay at rest? It'll start to do what? When there is a net force acting on an object at rest, tell me what the next line is.
Doesn't it move in that direction of the force?
Okay, I don't want you to say it moves in that direction. I'm not saying that you're wrong, but I want it better. Uh-oh. Are they coming to get you, Shannon? I hope not. When there's a net force acting on an object at rest, what will happen? Now, Shannon says it'll move in that direction, which is not, I couldn't count that wrong on a test, but there's a better way to say that.
It will accelerate in that direction.
It will accelerate in that direction. So it starts to accelerate. And because it's at rest, it will start to move in that direction, right? There will be a velocity associated with this, right? There's going to be a velocity associated with this box. So it starts to move, just like an object falls, this is starting to move to the north. But as soon as it moves, what does the Coriolis force do?
Deflects it to the right.
It deflects it to the right. So the Coriolis force is going to be a force that always does what to the motion?
Acts perpendicular to the right of the motion.
So do you agree the Coriolis force acts this way?
Mhm.
Now, there's going to be a formula, and we'll go through this the next day. We'll go through this on Tuesday. There's a formula. But now watch this. What will the object do now? What will the object do now? What will the air do now when this scenario, when the velocity is no longer 0?
It would move diagonally between the Coriolis force and the pressure
Which
gradient.
way is the net force pointing? So I tell you what, I want you to watch me because you can't do this. You won't be able to draw this, but watch. I'm going to erase this here. And now I'm going to put the Coriolis force up there. So what is this green right there? What's this? Isn't that the net force? It wants to go to low pressure, but it's turning to the right. And so the net force, so which way will the object, what will the object do? It will accelerate in that direction, which means it starts to move this way. Right? Now, is the Coriolis force, Zach, a real force?
No, it's a parent force.
It's apparent. It's not really there. It just looks like it is. Is there, what's the only real force? The pressure gradient force. Do you see that the pressure gradient force is acting parallel to at least a component of it to the direction of motion?
Mhm.
So what will the pressure gradient force do to this moving object?
Speed it up.
It'll speed it up. So the air starts to go faster. But do you agree there's also a component of the forces acting perpendicular to the motion, which will turn it to the right? Okay, now watch this. This is where it gets fun, and I wish I could do an animation. If the new velocity is this, which way does the Coriolis force work now? What does rule number 2 say? The Coriolis force always acts opposite the direction, always to the right of motion. Look at the Coriolis force, it's always changing it. So if we let it go, what would this object do? What would the yellow do if we continued the reasoning behind it? The object, if I did nothing but kind of let it go, would make a big circle. But it doesn't quite work like that, because the object keeps turning to the right. So what happens when the air turns to the right? So here's the thing. So do you agree that the Coriolis force is always perpendicular to the right of motion? Just so that you know, this is the velocity. That's the pressure gradient force, that's the Coriolis force. At this point, what would the air do? What do you think might be true here? Do you agree that it looks like this force and this force are pointing in opposite directions? So the pressure gradient force is equal to the Coriolis force. What's the net force?
0.
0. We call that geostrophic. Aaron, do you see that? Do you understand what I'm saying? So what's the net force acting on this, on the air now?
Wouldn't it just be velocity?
Well, no, the velocity is not a force, that's just the motion. What's the net force? 0, right? If these two forces are balanced, the net force is 0. So that means what will the air continue to do?
It would move inertially.
It would, this air would move inertially, which is in a straight line at a constant speed.
So in this example, was it already in motion? Is that why the yellow velocity is there?
No, well, okay, so what happened is this. The object was initially at rest. It started to move this way and then it turned to the right until it goes this way,
Oh, right, right.
right? So it's making the turn, but then it stays. And then what does it do? Do you see that it is now going to flow from left to right? Parallel to the isobars. So facts about the geostrophic wind so far. 1, 2, 3, 4, 5. The geostrophic wind is a balance between the pressure gradient force and the Coriolis force. It is an inertial motion. It travels in a straight line at a constant speed. It flows parallel to the isobars. It follows the Bayes-Ballot law. What's the Bayes-Ballot law? This was in your notes. This was one of your questions on the worksheet, right?
It says, with the wind at your back, low pressures to your left.
With the wind at your back, low pressures to your left. Do you agree that the wind would be blowing from left to right? Meaning, if you stood with the wind at your back, there's your feet. There's your shoes, right? And that means to the left is low pressure. And do you agree this is lower pressure to the north, higher pressure to the south? So what did the air want to do?
It wanted to move north.
It wanted to move toward, in this case, north, but it wants to move what?
To low pressure.
But is it moving to low pressure?
No,
No, because of what?
the Coriolis force.
So the Coriolis force makes the air become geostrophic. And then you've got all these things are true. Now, another thing that's true is that it is only true in the upper atmosphere. And the reason in the upper atmosphere is we assume that there's no friction. If we're near the ground, we have friction. So if I say, give me 7 facts about the geostrophic wind, you'd say what? You'd say the pressure gradient force and the Coriolis force are balanced. It moves inertially. It moves in a straight line at a constant speed. It is parallel to the isobars. It follows the Bayes-Ballot law, which states with the wind at your back, low pressures to your left, and it is only true in the upper atmosphere where there's no friction. That's 7 things. I've got one more to do, but we're not going to be able to get to it today. Does that make sense? Now, the pressure gradient force is -1 over rho dp dx equals 2 omega v sine phi. This is Greek letter phi. We are going to call this in the notes, it says this is case 1, which is linear upper level flow. Linear upper level flow. What we need to do on Thursday is we need to take apart what this formula means, because you don't know what this is, you don't know what this is. And we need to start dealing with one other fact about this. Any questions before I erase this? Because I want to show you something else. Any question? Okay.
You know, could you say that what, I'm sorry, could you see it? I couldn't read it. So it's, what is it?
What?
The
This?
second, the right hand of the equation?
This?
No, yeah,
Negative 1 over rho dpdx. Remember, that's the pressure gradient.
right?
And then 2 omega v sine phi. That's this thing up here, right? That's what the Coriolis force is. So what I'm saying, guys, is that the pressure gradient force is this. The Coriolis force is that. They're balanced. They're equal, going in opposite directions. Does that help?
Yeah.
Okay. Okay, so let's do this for a second. I'm going to show you one thing and then let you go. By the way, just so you know, the Chauvin trial, the jury's coming back in a few minutes. It's already, if you're interested. Okay, let me show you over here. Upper level winds. Here is what the atmosphere is going to look like. These are basically isobars. And notice that the wind is blowing parallel to all these isobars, with lower heights or lower pressures to your left. So in the upper atmosphere, when I see these maps, I know which way the winds are going to go. Do you see how close the isobars are here? They're stronger, there's higher winds. Over here, they're further apart and the winds are weaker. We know how to read the winds, right? So this is what we're going to talk about. We're going to give it some more stuff. But what I would suggest that you need to do for Thursday is you need to spend time in the book looking through geostrophic and gradient winds. And you also need to do a web search on gradient and geostrophic and gradient winds, because I want you to get really comfortable with it. To find some videos, spend about a half an hour kind of searching through stuff. You'll find some cool websites that have stuff, and we'll pull it apart and try to understand things a little bit more. Okay? So that's your assignment, and then whatever the chapter stuff is, that's due next week. Oops. I'm done sharing, and I guess that's it. Any questions? Did you learn anything today? Feel better about stuff?
By the way, did you get my email from over the weekend?
Oh, is it this Thursday?
Yeah, this Thursday.
Okay, so just review the lecture. We'll miss you.
Okay.
Okay. The rest of you will see Thursday, and Isaac, I'll see you next Tuesday.
Okay.
Thank
Have a
you.
good one.
Thank you.
Bye.
Right.